Good morning to one and all. I welcome all of you to first session of third day. I am Basaraj Patil, Assistant Professor, Department of ECE, VTU CPGS Kalaburagi. Feels pleasure in introducing an eminent personality to all of you, and he is Dr. Prashant Kumar Sahu, Associate Professor from Indian Institute of Technology, Bhubaneswar. So, let me first present you a glimpse of his achievements. To begin with, Sir completed his PhD in ANC in the year of 2008 from IIT Kharagpur. I would like to add that two candidates have completed their doctorate under his guidance, and three of them are still continuing their research work under him. He is an institution himself. He has published 27 papers in international journals. He has even participated in 35 international conferences. He has also penned for 5 chapters in the reputed book. Finally, the very special part of about him that Dr. Prashant Sahu has been awarded with 8 honors and awards. Few of them are Senior Member of Optical Society of America in 2018, Fellow IE1 in 2018, Member of ISSE in 2017, Member National Academic of Science India in 2016, and Fellow in IETE 2013, Senior Member in IEEE 2012, Life Member in 2010, Indo-Italian Research Fellowship in 2007 to 2008. Thank you. I request all the participants, please turn off your mic and switch off your camera. Now I am handovering the session to carry out by Dr. Prashant sir. Thank you, one and all.
Good morning to all. I hope I'm audible. Oh, yeah, thank you. So let me thank you to the entire team of VTU for inviting me for delivering this talk. So today I'll discuss about optical communication technology, possibilities and challenges. And if you have any queries, you can ask me at the end, or you can send me by mail or a message so that I can reply you. So just 1 minute. Okay, so now under this talk, I'll cover some portions like introduction, the optical communications, signal noise and interference, signal propagations. So our ongoing research activities, including the applications, some of the challenges, opportunities, and finally conclusion. So when you say about communication, most of us know that basically it's a process of, or it's a way of exchange of informations. So this communication history is a very long history. So I'll not go to those long history. Rather, I'll start with a history that spans over the last 50 years. So I'll try to compare over the last 50 years how the communication technology has grown and where this optical communication has a role to play. And then I'll say what are the challenges this optical communication offers and what are the opportunities, or you can say what are the possibility for the future generation or for the coming generation to take up research in this area of optical communication. So well, now if you go to the brief history that I just say about 50 years back, 1970, so the communication with 100 Mbps was possible. So at that time, the bandwidth distance product was achieved as 100 Mbps per kilometers. That was the upper limit, or you can say the threshold that has been achieved at that point after a long-standing research. They reach a bitrate distance product of 100 Mbps kilometers. in 1970. And then it was found that the speed was limited by the fundamental limitations of electronic circuits, which cannot be further pushed up. However, curiosity, people still wants to have more bit rates, more bandwidth. To achieve this, the research was going on. And it was realized in the second half of the 20th century that it is possible to increase the bandwidth distance product, what we call as BL products, beyond this 100 Mbps. If we, and that too, not only one or two orders, whether several tens of orders was possible. And there comes the need of a carrier, that was your optical carrier. So you can say that the research phase of fiber optic communication started around 1975. So at that point, if you read the contemporary literature, you will see that is the era at which or around which the lasers, the high power lasers were invented. So the optical fiber along with the lasers has given a platform to design a new mode of communications, what we call as light wave based communication systems, or you can say optical communication system. Well, now, so as I said about the possibilities in this optical communications, where around your 1970, it was observed that 100 Mbps. Now, if you see the plot here, it's from 1980 to 2010. So over this period, if you see first 40 years, so the 70 period I removed there, it's only 100 Mbps. So now if you see from 80 to 2010 or 30 years, you can see, hello, you can see that the research and the commercial spheres, you can see the space. So where the bitrate distance product is shown by this plot is squares shape plot indicates the research contributions, and this is what the commercial activities, or you can say commercial realization of the high bitrate systems. If you see around 2005, it has been seen that the research and your commercially viable solutions are almost converging. The bit rates of few terabits were possible. So we moved out from a scenario whereby the bitrate distance product was only 100 Mbps kilometers to your terabits per second per kilometers. So that's what achieved around first part of your 2000s, or in the first half of the first decade of 2000. We are in an era whereby, so we said about terabit communications. So now, so when you say about this megabits per second, gigabits per second, and then to terabits per second, so this all means the bitrate at which the system is able to transmit the informations. So now that indicates that we need to design a full-fledged communication system. So when you say about a full-fledged communication system, so what are the design factors? The basic design factors are like the bandwidth. So higher is the bandwidth, higher is the bitrate. This is an obvious factor. But you know, the bandwidth is limited in other medias like a twisted pair cable or in coaxial cable. That is due to the material properties. However, in optical fiber, it is possible that we can reach up to terahertz of bandwidth. I'll come there. How do we calculate this terahertz bandwidth? And next design consideration is the transmission impairments. That's about your attenuations. So this attenuation limits the reachability. So now fiber or optical where you see the attenuations are not the same in all these three form of guided media. So the twisted pair cable offers the maximum attenuations. Coaxial cable are better than that. In coaxial cable, the attenuation is the order of 5 dB per kilometers. Whereas when you see about optical fibers, you'll see that this is dropped to 0.2 dB per kilometers. However, some companies interference from competing signals in overlap frequency band can distort or wipe out a signal. This leads to two form of interference. One is your inter-symbol interference, other one is the inter-channel interference. So I'm giving a brief background before I move on to the optical part. Now next is what the other design consideration is about here, point-to-point link or a point-to-multi-point link. But once you increase the number of attachments, each attachment will introduce the distortions and the attenuations, and thereby limiting the bitrate and the reachability. So you can say, so your BL product will remain constant. So if you want to extend over a longer distance with this constant, your bitrate will fall, or vice versa. So these are all the design factors to be considered to design to any communication system, not only optical. Now again, going back to that that graph what I shown you about the bitrate part. So here if you see that around 2000, this in the first part of the first decade of 2000, the capacity was attained up to 2.56 terabits per second. This was achieved using a technique called WDM. So they have used 64 channel WDM at a bit rate of 10 Gbps and used 4 fiber pairs. So totally, if you count, it's coming something around 2.56 terabits. So that was the backbone part. So similarly, if you compare this digital hierarchy part, you can see for OC768, so we are reaching a bit rate of 40 Gbps. Similarly, for OC192, we can see a bit rate of 10 Gbps. So I just stopped here at 40 Gbps because in Indian context or in ASEAN context, most of the countries are with a 40 Gbps backbone. Whereas if you see your Europe or America, you can see that terabits backbone link is available there. But in Indian context, it is 40 Gbps. People are working how to further increase the backbone from 40 Gbps to terabits, but it is not yet realized in India. So now next, if you see, this is the complete frequency spectrum that is being used for communications, but our interest is from this band, that is the optical transmission band 3 terahertz to 300 terahertz. And based on this, the next slide you'll see the subbands in optical communications, like the UVC band, ultraviolet communication bands, visible light band VLC, and your infrared or your near infrared band. So most of your communications are using optical communications are using near infrared. So the frequencies wavelengths are 1330 nanometers or 1550 nanometers, but most of the service providers are moving towards 1550 nanometer. So besides this guided mode of optical communications, optical communication also offers one more wing, what we call as optical wireless communications. And there the bands are, for free space optical communication, it is from 750 to 1600 nanometers. For VLC, it is 390 to 750 nanometers. For ultraviolet, it is 200 to 280 nanometers. So after having a brief intro about, so what about this communication? What are the spectrals? What are the bitrate possibility? And which band we can use for optical communication? Now let me come down for a motivation. Why do we need to do research or to carry out studies in the area of optical communication? So if you see, only if you analyze the Scopus, the published articles in Scopus year by year. So this is an analysis. So I made again first 50 years analysis, 1970 to your 2020. If you see around 1970, the number of papers are less than 10. But if you see the trend, it is increasing, and by 2019, so 2018, if you see this plot, 2017, it reached more than 4,200 papers per year. And in 2020 till date, already something around 1,200 papers are published in this optical fiber communication area. So this gives a feel that this area, a lot more thing can be done in this area. A lot of possibilities are there. And if you see as a whole for the optical communication, you can see that till now, till date, from again 1970 to year 2020, something around 3,71,000 articles are published. that includes all areas, communications, medicals, sensing, and all together. So this optical fiber based system designs has a lot of potentials, a lot of scope to work on. Now, if you see this slide, here I've shown based on the same statistic of the 61,876 papers. So I try to distribute them according to the country of origin. So now if you see, most of the papers were published from United States or from China or Japan or from UK, Germany and France, and also Italy and Canada. But if you see the contribution of India over the last 50 years, for this 61,876 articles, you'll see the number is only around 1,600. So this indicates that in India, the number of groups working in optical communications are limited. So we should expand this research area. We should make this reach in all different institutions so that people can take up this area as a potential area of research. So it is having a lot more to offer. So after having a brief idea about what are the ongoing things across the world and what are the possibility in publishing articles in this area, not only publishing the articles. So I didn't included other articles that are not a part of the scopus. So there are many journals are there, many articles are publishing every year, but I have taken only the reputed papers and the reputed journals, and this analysis has made here. And now this is what I was telling. So something around 3,09,135 papers are there in optical fiber related areas. So this includes communications, sensors, healthcare, and so on. So now here again, if you see, the number has gradually increased. So now every year in this domain, optical fiber domains, more than 10,000 on average papers are getting published since 2010. Since 2010, if you see constantly, more than 10,000 papers are publishing every year around the globe, that too in good standard journals. So after giving a brief on, so what are the cases related to this optical fiber-based communications or optical communications, a lot of opportunities are there. Let me go down into the optical communications. I'll try to figure out some of the problems during this discussion, and I'll put forward a few challenges that one can take up as their research further, as their problem further for future research. So now going back to the very basic communication system, you can see that just like your normal communication system, for optical communication also, we need to have an optical transmitter, a communication channel, and an optical receiver. So now here I'll try to concentrate more into the optical fiber section. So if you see, the optical fiber is a normal architecture of a fiber, whereby you'll see the core diameter vary from 8 to 100 micrometers, depending on it's a plastic or a glass fiber. The cladding is the outer part of the core, and how to distinguish the core and the clad, you'll find there's a refractive index difference in the core and clad, and that's the reason that light is getting guided within the optical fiber. And outer layer we call as the jacket. Now when you go to the market, you see that we're having a different varieties of plastic fibers. These plastic fibers are mostly used for your decorative purpose, not for your communications. Whereas different grades of glass fibers are there, which are being used for your communications. You can go single mode fiber, you can go with a multi-mode fiber, and so on. So now when I said about the types of fiber, about the single mode and multi-mode, it's a well-known fact that most of the communications are around your single mode fiber. The reason behind is that the lower attenuations offered by your single mode fiber around your 1550 nanometer window. But now I'm going to introduce a specialized kind of fiber, which is not exactly a specialized fiber, rather it is a form of your multi-mode fiber. So what we call as a few mode fiber. And this few mode fiber has got two configurations. One is the uncoupled multi-core fiber and a coupled multi-core fiber. So now here you may ask, so why do I'm bringing this multi-mode fiber which is not being used for the long distance communications? The reason being we bringing here this multi-core fiber, or you can say few mode fiber, is that the single mode fiber already attained the theoretical limit in terms of the spectral efficiency, what we define as bits per second per hertz. So this limit is due to the nonlinear effects in single mode fiber, what is otherwise known as Shannon's nonlinear limit. So we cannot push this limit beyond that threshold. So that's the reason that we need to have a alternate to single mode fiber to have a higher spectral efficiency than the existing threshold of your single mode fiber. So in other words saying, how to increase the capacity of single mode fiber further. So to that question, the answer is what? We need to go with a multi-core fiber. But when you use the word multi-core fiber, and I'm saying multi-mode fiber is not being used for a long distance communications, then the next immediate question comes, why do we need this multi-core fiber at all? Well, we lay a good number of single mode fiber, so by that way we can increase the capacity. Well, this is possible to lay large number of single mode fibers, but the problem is the laying part. And then why do we need this multi-core fiber then? The multi-core fiber, you must have heard about the data centers. The data centers transmits gigabits, terabits of data over a channel. So now this channels, which is basically the single mode fiber, is getting saturated. So to interconnect the data centers, which are basically over a distance of few hundred meters, we can use this kind of multi-core fiber. So the huge data volume of data centers can be handled by using this multi-core fiber. So that's what the good part of this multi-core fiber. And this multi-core fiber supports your mode division multiplexing, as well as we can also implement the space division multiplexing using a multi-core fiber, which is not possible over a single mode fiber. So this is what the basic foundation behind reconsidering this multi-core fibers. So this is a new area of research. People have forgot about multi-mode fiber since 1980s. Now again the trend started since 2016-17. So you will see that some of the groups have started working on this multi-core few mode fibers to solve the problem related to data centers. But it is also possible to reduce the attenuation in this multi-core fibers. So some more research is required in that area. Now, so if you see the benefits of the fiber, it's again a well-known fact, nothing new. It can support hundreds of gigabits of data, maybe terabits. Its size is small and size is small, weight is less, slower and offers lower attenuations. It is free from EMIs. It supports very large repeater spacings. When you say that big distance products, so that distance is basically the distance between the repeaters, or what we call as the repeater spacing. So now for this bit bandwidth distance products, the distance between the repeaters can be of the tune of hundreds of kilometers. I've given you a tens of kilometers considering a worst possible scenario, but in most of the commercially realized cases, you will see the repeated distance are hundreds of kilometers. So the application of the fiber, it supports multi-domain applications, starting with communications, sensing, your LAN, WAR connections, LAN and your FTTH connections, healthcare applications, and so on. So now this is what I was telling some minute before about the attenuations. If you see this windows, you can appreciate that it is a 1550 window, which offers the lower attenuations. So in most of the fibers, most of the service providers are now switching from this 1330 window, which is a second window, to your third window. Most of the countries, it is already operating over this second window region. However, in the whether you select second window or the third window, the attenuation what I shown you, that was the inherent or intrinsic attenuation of the fiber. But fiber also get exposed to a number of types of environments, and this environments leads to additional attenuation into the communication. So now here if you see, this is a special case whereby soon the fiber is being passed through a region where there is a effect of your radiations. So now if you increase the radiation loss from say 0 to 10,000 psi, you'll see that the loss is increasing from almost 0 to 5 dB per kilometers. However, this radiation induced loss is time dependent. If you increase the exposure period of this fiber to a period say around 10 to 5 seconds, you'll see that the attenuation is no more 5 dB, rather it is around 1 dB. So whenever somebody designs a network, they have to consider the link budget. And under link budget, one has to keep some margin, the link margin, so that the reachability and the quality of the signal. So here basically the bit error rate should not fall below the allowed threshold value. So for optical communication, we need at least a BER of 10 to minus 9. So again, now this plot shows your overall loss over the different wavelengths. So you can see here that around 1550 nanometers and 1330 nanometers will got to lower loss windows. So including this includes your attenuations, the absorptions, and the scattering losses. So this is what is obtained. So now beside this losses, the other form the loss what fiber get exposed to is due to the laying dimensions. So it is not possible to lay the fiber always on a flat surface. You will see this fiber sometimes gets laid over a domain, over a terrain which is not straight, rather it's having some curvatures. And that curvature leads to a loss, because if you see here, the power is lost due to the radiation modes, what we call as the leaky modes. So the power from the core get leaked into the clad, and due to this decaying modes or the radiation modes, this power gets lost over time. And this span over which it lost is very small period. So we are having a loss of the power from the optical fiber itself due to the terrain over which we laid the fibers. Similarly, because of micro bending and macro bending also introduces loss. So here I've shown you the losses due to micro and macro bendings. The next detrimental effect of signal communication over optical fiber is the dispersion, which is regarded as one of the most dominating mechanism besides your nonlinearity. So here you see we got a sequence of pulses. With the passage of time, the pulses are getting spread out. So here you can see that these pulses are here so clearly visible, distinct, but here they are no more distinct. They are barely separable. Now if you see here at this point, this looks like as if we are transmitting a single pulse. So this is what is called a pulse broadening effect, so which is otherwise known as a dispersion mechanism. So this need to be addressed. Besides that, we also have a PMD loss, that is what we call as a polarization mode dispersion. So due to the varying wire fringes along the fiber, you will see that the polarization of the light changes, and this introduces the polarization induced loss, what we call as PMD. Then this I've shown you a case. Many people are working on this dispersion management schemes, whereby they're trying to flatten the dispersion curve or they're trying to shift the dispersion. So in this plot, I've shown both the scenario. You can see 1300 nanometers, you'll see you having a zero dispersion region. This can be shifted towards your 1550 nanometers. Similarly, we can also have a dispersion flattened case of a fiber. So there are different mechanisms are there for dispersion compensation. One can use a dispersion shifted fiber, one can use a dispersion compensating fibers, or one can also work with fiber Bragg ratings. So if you recall in one of the slide, I say the dimension of the fiber varies from 8 to say 100 micrometers. So the mode field diameter also plays a role on the different losses and on the dispersion. If you see here, I have shown the three cases of 6, 8, 10, and 12. So whereby you can see for different mode field diameter, the effect of dispersion and the region of operation also varies. And now here if you see, so here this is the original basic fiber loss without including your micro bending and a macro bending loss. But now after you include the micro and macro bending, you can see the losses are sharply increasing. You can see these two curves. Here I have shown you the effect due to the micro bending is this one where the attenuation has reached up to 2.5 dB per kilometers, and this one is due to macro bending, which is also more than 3 dB per kilometers. So these all are different detrimental effects need to be addressed while designing an optical fiber based system. Again, I've shown you the micro and macro bending cases whereby what is a loop diameter. So for loop diameter and for the coupling length, you've got the different losses, which is ranging up to 2 kilometers. Now, after knowing about this detrimental effects, one more problem with fiber-based communication or a fiber-based system design is that how do we couple the light into the fiber? So basically, most of the source are modeled as a Lambertian source. So for a Lambertian source, if you see here, the acceptance angle is quite large as we go away from the source, but the launching to be done near to the source. So at this point, when you see when the light is launched into the fiber, so all the light is not able to guide it within this acceptance angle. So a part of this is always leaked into the cladding part, which will be lost as a decaying mode or a radiation mode. So the power that we are able to launch into the fiber is not what is output from the laser. So a good part of the light output from the source is getting lost due to this nature of the light source, Lambertian nature of the light source. So there are opportunities are there so as to work in the area of the sources also besides the entire communication system. So after having an idea on this problems on fiber-based systems, so one more thing everybody should note, when you why this single mode fiber or multi-mode fiber, the transition taken some time during your AKs. Not only because of the loss and attenuation, but also there was one more issue: how to splice the single mode fiber, because the dimension was varying from 8 to 12 micrometers, and there was no modality to splice the fibers at that point, because the splice induced loss were as high as 5 to 10 dB at that time. So that's the reason that people were trying to do more work on multimode fiber around 1980s. But around 80, 81, this low loss splicing techniques were developed, what we call as the fusion-based splicing, and the loss as low as 0 dB was possible. And thereby, the possibilities of using multimode fiber for communication was almost gone from the market. But now for a single mode fiber, though I say the loss is 0 dB, but when you splice it or when you interconnect the fibers using either mechanical connectors or the fusion splicers, you have some issues. The issues are, it may so happen the fiber got a lateral shift, it may so happens there is longitudinal separations are there, or maybe an angular shift. So these three forms also lead to additional loss in the fiber. So though the engineer, whoever has designed the network, may have planned properly, but due to this kind of breakage or interconnection of the fiber links in after the design period. So it may happen that the reachability may fall. So in the design part itself, we need to keep a good power margin or the link margin for designing the overall power requirement of a optical based system. So now here I have characterized some of the commercially available fiber with their effective area, the zero dispersion wavelength, the dispersion and the slope. So basically if you see here, this beta 2, this is the dispersion and beta 3 is the dispersion slope. And this beta 1 is basically is the propagation constant, and this depends on the group velocity. So now if you see this table, so you can see that by reducing the core effective area, we can able to reduce this dispersion. So it was initially with a 80 micrometer square, it was 16 to 19, but now with say around 72, it fall down to 2 to 6 because it per kilometer nanometers. Similarly, the dispersion slopes also reducing. So now the point here to mention that it's better to have a small effective area rather to have a large effective area. But when you say small effective area, then the problem is the light coupling. So there what the trade-off is. So one need to think about how to counter this. So this also is a possible area of research. Now next is about why do I'm saying about key single mode fiber, though it offer terahertz, but still the bandwidth is not sufficient. We need to find some alternate modes. The reason is that why do we need a large spectrums? The basic answer is that with Shannon channel capacity, if you see this W log to 1 plus S by N defines the number of bits that can be transmitted over a given channel. And this W is the frequency range that the media allows to pass. In your optical fiber case, if you see the scalar frequency, optical frequency around 1550, it is 193 terahertz. So if you take a fraction of that, say something around 10%, so it's around 2 terahertz. If you take 20%, it's 4 terahertz. So 20% is good enough. Till now, only 20% of this scalar frequency is being exploited over the optical fiber. That's why I use the word 4 terahertz. We can exploit up to 4 terahertz bandwidth over a single mode fiber. But this bit spectral efficiency is now almost reached the threshold limit. That's why we need to have more number of single mode fibers, or we need to try for new kind of fiber where we say we can go with the this few more fibers or a multi-core fiber. So this is for a source point of view. When you use a LED source and a laser source, you'll see the power variations are different. LED offers a low output power. These are not coherent. And the light what you get from the LED will be get lost over a smaller distance. So this is basically suitable for your short distance communications. So here by varying the bias current, we can change the output power. And also you can see here by varying this, you also have to look into the power, the temperatures. So what we need to maintain, otherwise the source lifetime will be reduced. Similarly, same is true for the, we can also produce the different output power by varying the bias current. And here also we need to maintain a thermoelectric controller so as to control the temperature. And this is some of the receiver part. So I'm trying to show you the possibility in the source, in the channel, and in the receiver section. So this is about the receivers, what is available in the market. Basically, most of the receivers are based on the pin or APD. So I've shown the case of the pin. So we got the 3 different material-based pins like silicon, germanium, and InGaAs. So the possible wavelength over which it can respond, and the responsivity and the bandwidth you can see. So in most of the cases, so your receivers are bandwidth limited. So this is the bandwidth limited cases. So we need to see, though we have got a huge bandwidth, but due to the receiver limitations, we may not exploit the entire available bandwidth over a single mode fiber. So possibilities are there to work on how to further increase the bandwidth of the receivers. So now, so let me again back to the communication domain. So in the communication domain, when you propagate a signal, it suffers from noise and interference. So now we are hearing some noise. So noise is what? It's unwanted signal cases, some kind of background radiation. So this is there in both your wide and your wireless communication, optical communications. We also have the interference from adjacent channels
ನೋಡಲ್ಲಿ
and overall signal to noise ratio you can see as signal power by noise plus interference power. So this is about your other fundamental effect in your optical based communications besides the inherent property of the fiber and the media. So now when you analyze the signal, you will see that there are three broad cases are there. One is a transmission range, one is a detection range, one is a interference range. So the transmission range decides the reachability of the signal, and also it says up to what distance you can attain more coverage. Similarly, for the
ಎಲ್ಲಿ
detection range, you can see
ಎಲ್ಲಿ ಹೋಗ್ಲಿ ಗೇಟ್
over which
ಹಾಕ್ತಡಿ ಎಲ್ಲಿ ಮನೆಗೆ
the signal can be detectable. Finally, if it is a signal for the interference range, you may not be able to detect the same.
ಯಾವಂತಲ್ಲ
This is what you see for a wireless scenario. So optical communication is not only confined over a optical media, but also possible using wireless scenario.
ಎಲ್ಲಿ ಅಲ್ಲಿ ಮಳೆ ಬರಕತ್ ನೋಡಲ್ಲಿ ತಗೊಂಡ
So this is different cases of this wireless scenario whereby the problems are like shadowing effect, the reflection, the reflections, the scattering, and the diffractions. So, and when you see the power analysis over a wireless scenario for optical domain also, you'll see the power is varying as 1 by d square. So this is again one more problem. So unlike your optical fiber where you can reach over a longer distance, using optical wireless, we cannot reach a longer distance. So how to improve the reachability, that is again a point of discussion in optical wireless domain. So this is what different cases of the um, detrimental effect for a wireless scenario, what I just now told. So now, based on this, I can say I can have a time dispersed channel whereby I will have the inter-signal
ಹಾಕುವಲ್ರಿ
interference.
ನಡಿ ಹೋಗೋಣ ಅಪ್ಪಾಜಿ
Or the other case
ಬರೋ
is
ಮುಂದೆ
the
ಬರ್ತಾವ
case whereby I get a phase shifting. So that results in the distorted signals. And besides that, we are also having an effect called fading. So fading, we may have a slow fading or a fast fading. So there's a short-term fading, it is a long-term fading. So this is again one more channel impairments for a wireless scenario. So for a wireless scenario, when the distance between the sender and the receiver increases, this problem will be more severe. Or if the obstacles is away, then also this problem will be there. So fading will be again just like an inherent problem for wireless scenario. As I said, attenuation is inherent problem and nonlinearity. The same is true for the same in the same line. I can say fading is there for your optical wireless, or you can say it's the equivalent of that dispersion in optical fiber based communication. So now here if you see for a optical system, wireless system, you can have the path loss. Obviously, that is your 1 by d square will decides. Besides that, you'll also have a relay fading and a shadow fading. So these are some of the challenges that needs to be addressed. Now for a optical networks, if when I say, so it can satisfy the growing bandwidth demands, we can switch from one fiber to other fiber, or we can incorporate more number of fibers. And it supports the protocol transparency, what is not available in other medias. It is reliable and it simplifies the network operations. And with the invent of this DWDM and WDM, we can see that we can implement arbitrary topology. We can implement a transparency of protocols onto the fiber. We can have reconfigurability, survivability, scalability, and your modularity. This all being supported by the current generation optical networks. So now, to meet the demand of this growing demand of the multifaceted communications and multi-dimensional communications where internet plays a role, So we need to provide access to information when, where, and whatever formats. And to meet this demand, it is the optical fiber and optical wireless together will play a complement role to each other. The reason is that the optical fiber doesn't go everywhere. Wherever it goes, it provides a huge amount of bandwidth and offers a number of advantages in terms of transmission properties. Whereas optical wireless, if you see, it cannot go over a longer distance, but it cannot go over a longer distance in the sense the reachability is low, but it can go almost everywhere and supports the mobility. However, it is susceptible to different environmental parameters, like I said about the fading and your the inter-symbol interference. And besides that, the major problem in optical wireless is its your environmental effects. So now let me summarize this optical communication as a whole into this figure. So if you see this figure, so it is very much understood that though we have a gigabit or a terabit network, but if you see the access points, the interconnection points, where we got a bottleneck. So it is getting scaled down to few Gbps or few Mbps. And if you see for a LAN scenario, though we got gigabits LAN, but most of the cases it is only 100 Mbps. So though I have a huge super highway, but if my interconnections are using, say, rural roads, then the traffic what this network supposed to support is not going to support due to the bottleneck of this access technologies. So now there is a plenty of opportunity to work in the access part of the communication system. So after saying this much, let me now say something about what we are doing on. So our group is basically working on this long range optical system designs. So we are also working on fiber-based remote sensing systems for basically structural health monitorings. So we are also working on this healthcare support using optical fiber-based systems, FSO system modeling and attenuation analysis. So on flying network platforms, how to incorporate UAV and drone into a network of flying object so that this can be used as a backbone for this FSO. Besides that, this VNet, or you can say intervehicular communication using free space optics. Now, some of the results I'll show from this, from some of our groups work. This is one of my students' work. So basically, he was working in this. He's working in this FSO designs. He'll submit his thesis soon. So now, if you see here, so the result shown is about what are the detrimental effects on a free space based communication. So now for a FSO, so we consider the effect of the scattering, the rain, the turbulence effect, and the geometric misalignments, or you can say the bore side errors and the misalignment errors and different turbulence. So here the losses are mapped over a distance. And you see this y-axis is in the loss in dB per kilometers. If you see it around 10,000 kilometers, you'll see the losses are very high, of the order of say 50 dB due to the rain, and 45 dB due to scattering. Geometric loss is something around 15 dB, and your turbulence is more than 20 dB. If you take all together, you'll find the loss is more than 100 dBs. So you'll not have any system that can support this kind of a free space communication. So you need to launch very large amount of power, or you need to find out a advanced modulation format whereby you can say that well, your system is rugged against this environmental factors. Similarly, so this is the architecture on which he was working, and this is the again the different scenario of this FSO system for a bit rate of 1 Gbps and 10 Gbps by varying the divergence angle from 1 milliradian to 4 milliradians, and aperture diameter was maintained at 25 centimeters. You can see the results, how the Q factor is varying. So the acceptable Q is something around 6.2. So you can see here that this is the line that shows 6.2. So up to 2 kilometer we can reach. And similarly, this is for a 2 kilometer span only, the same result has shown. How good we can achieve these values, what are the Q factors, what are the distance, and what are the aperture diameter that we need to implement this kind of a FSO link. However, this FSO link, as I say, suffers from this different environmental effects. So we have shown here a hybrid system whereby the issues with optical wireless can be resolved using a RF and vice versa. These RF systems are more susceptible to your this rain and the weather, whereas FSO is not. So we can use this as a complementary technique. So now I'll not go into that because of time constraint. This is the outage probability for a system without using any diversity scheme. And this is using a diversity scheme. So now this is what I want to highlight here. So the major challenges are how to optimize the channel capacities, how to incorporate this space division multiplexing, or what I was telling about mode division multiplexing over this optical fiber, so that we can enhance the spectral efficiency, or we can push the nonlinear Shannon's limits over the fiber. The second part is how to make a reliable link, how to take into account the different effects over a wireless communications, optical wireless, like the beam divergence, the receiver aperture, the unfavorable condition of the atmosphere, and the received signal quality and the power. Finally, the unreliable and unpredictable link. So after this, so now the different opportunities where one can work in this area. So I'm listing here. So one of the very prominent area we started very recently around 2018 is machine learning for optical networks, whereby we can address the issues of the optical switchings, the channel selections and the switching. Similarly, for the optical wireless, one can think about the cybersecurity vulnerabilities. How can we address that? The next is the transmission of multi-dimension signals. This is again a very hot topic of research. How to develop different algorithms so as to optimize the transmitted powers and the divergence angle for a optical wireless scenario. Underwater and unmanned aerial vehicles using optical wireless techniques, advanced digital modulation techniques, the PCA-based system design, but PCA-based systems are not very much suitable for your communication, but this can be designed for your sensor systems. Similarly, how to design an optimize indoor application using VLC and your MIMO ODM. This VLC is already in some places in use, but now the work is towards how to implement massive MIMO ODM over this VLC communication. So finally, so I'll conclude by saying that the opportunities in your optical communication is a lot of opportunities are there. The research challenges are multidimensional in nature or multidisciplinary in nature. And these areas ranges from device physics to communication modeling, signal processing, communication theory, algorithm developments, as well as the computer sciences. So all these areas people can contribute to the optical communication or optical system design and developments. So one can think about, so in summary, I'll say one can think about developing various multi-core fibers for SDM transmissions. We can use the existing communication technology for the yet to emerge smart communication, like your smart grid communication and smart grid applications, or you can say other form of smart communication. And we need to do more research to overcome the challenges of optical communications to realize a large scale terabit communication so the end user can get at least gigabit connectivity. So with this, these are the references. Thank you. So this is all about today's talk. Now, if any questions are there, I'll be happy to answer.
Hello. Hello, sir.
Hello. Hello. Yeah, I'm audible. Yeah, I'm
Hello,
hearing you.
it's me, Amarnath. It's me, Amarnath, research scholar under VTU. Okay.
Okay.
My topic is cloud security. you have said something related to cyber security vulnerabilities for optical networks. These are all the opportunities in the research. And how is the scope for the future researchers in this field for computer science researchers?
That's why I'm saying right now, see, the cyber security vulnerability is a major challenge. So no country can claim that their infrastructure is 100% secure from the cyber attacks. So I'll give a very simple example. I will ask about how the computer engineers will play a role into this. You must have heard about the smart grids, this electrical grids. So in many of the countries now, the grids are interconnected. If a cyber attack happens, the entire grid will be down in a fraction of a second. And that will lead to the catastrophic failure of all the computational resource, including your banking, data centers, all the database. Okay, not only the power grid, that will have a cumulative effect. So how to design a resilient network that will be free from your this cyber attacks. For that, one of the solution is what we can migrate from the conventional RF or this coaxial based communication link into a either a fiber based secure link or on a OWC based your optical link for communication. So once your communication network is safeguard, so the grid will not be failure. So and once the link is not grid is not failure, all other resources will be intact. So this is one application of your this optical communication into this cyber physical domain.
And how about the most of the research is going on in the radio frequency and radio waves. So we are using Wi-Fi, WiMAX, and some of the companies are implementing more money on these wireless technologies. And how can you justify that optical communication networks helps in a wide area compared to wireless networks?
That's true. About the RF is a mature technology, but the main problem with RF is that the wireless data transmission speed, if you see, we can attain at best 1.8 Gbps using your MIMO technique. Whereas if you go with your optical wireless, you can go several of tens of your gigabits. So that is what the first advantage. So if you see in one of the slide, I have said we cannot reject RF directly or in the immediate future, but we can use these two as a complementary technology. Your RF signals are highly affected also by the environmental factors as your optical signals, but the effect is not same for both. Like your clouds and rains affect your RF the most, whereas fog affect your optical signal the most. So if you use this as a complementary technique, means in the absence of one, the other will be available, then you can attain a high bitrate scenario for all weather conditions. And if you see the current 5G, in the current 5G and 6G, people are moving towards this optical wireless, where a very good example is this VANET, this interconnected vehicles. So now all these automobile companies are working on to include this optical wireless module for their VANET applications, because that is more secure as compared to your RF signals. Because tapping is possible over a RF signal than on your optical signals.
Okay, nice example, sir. Thank you. And like if the industry of VANETs is growing, does the researchers or else the software professionals or else one who is working on this particular technology is having a wide scope? Okay, and okay. Thank you, sir. Thank you.
Welcome. Yeah, any other questions?
Yeah, good afternoon, sir.
Good afternoon.
Sorry, good morning, sir. Sorry, good morning. This is Shashidhar from Shanbasa University, Kalaburagi. Sir, you said that one of the research opportunity in optical fiber communication is that using machine learning, sir. How I can use machine learning in optical fiber communication, sir?
Yeah, this is again. If you recall, I said that it's a very recent. There is a very recent work in 2018 onwards. Some groups have started working on application of machine learning on optical communications. Basically, when I said about the switching, the routing, so now this is a major challenge in your optical communication, because if you see the data transmission rate is terabits. Most of the
Okay.
backbone supports terabits. So there, how to incorporate the switching and the routing. So there comes the role of the machine learning. But till 2018, no group has started working on this machine learning. It is a very recent work. It started over the last 1.5 years. So no more, means not much of the information is available in this area. So that's why I say it's a area, it's a new area to work on.
Okay. Okay. Thank you, sir.
Welcome. Welcome. Thank you. Thank you. So, okay. Thank you. Thank you. Thanks a lot to all of you for joining this session. Let me thank again my friend Dr. Sanjay Gore and his friends of VTU for inviting me for this talk. Thanks a lot to all of you. Thanks all participants. Bye. Bye. So I'm logging out from here. Thank you.